Hi, I'm Kip Degeorges, and this is an exploration of on-discriminative versus generative classifiers by Ing and Jordan, published for NIPS in 2001. Ing and Jordan's paper compares the behaviors of the two titular types of classifiers as they model a given data set of increasing sample sizes. Uh, they start with two pieces of folk wisdom, known in popular data science. One is that the discriminative method is just more efficient at modeling a classifier than the generative method due to how the former directly models the posterior probability. The second is that the number of examples needed to fit a model is roughly linear to the number of free variables in the model with some coefficient. Uh, this is at least true when it comes to discriminative classifiers. By analyzing both of them mathematically and graphically in terms of how they grow as an increasing sample size and accuracy, they set out to examine whether these assumptions hold up, where those assumptions don't hold up, and where more nuance can be found. The paper focuses on two types of classifiers that I already cover in class, but I'll go over them again just to make sure. Logistic regression is a discriminative probabilistic classifier for modeling the posterior probability P of y given x. Naive Bayes is generative, and it models the joint probability P of x and y, and then uses Bayes' rule to then compute the posterior probability. A major relationship that the paper establishes between the two classifiers is their asymptotic errors. That's the error of each model as they are given some arbitrarily high amount of sample sizes that the error can't reduce anymore. Uh, in this case, it's shown that the asymptotic error of the discriminative classifier is less than that of the generative classifier, which means that at some arbitrarily high number of sample sizes, discriminative will be more accurate than generative. And that's often why they say that because of the direct probability modeling, the go is discriminative over generative, it's going to be more accurate. That is, again, the folk wisdom, and is kind of reasoning behind it. The second major comparison is a characteristic called accuracy growth, or how the error grows negatively. They express it as this equation. The error of a given model is less than or equal to the error of that model, the asymptotic error of that model, plus some constant, representing the fact that it hasn't reached its asymptote yet. Uh, that constant can also be described as a big O function, O of M and N, where N's the number of variables in data set, and M is the number of samples needed for the classifier to reach the asymptotic error. Uh, Big O notation is a sort of function used in data science to describe algorithms and models at a certain rate in terms of usually just O of n that grows with the model. Uh, Sometimes it could be O of log n, sometimes n squared. And then in this case, we want to use a solution for m in order to find where that O of m and n term becomes O of 1. We'll see that's how we prove. We'll see that in a second. So for example, for discriminative classifier, we have the error of the model is less than or equal to the asymptotic error of the model plus the O function of square root n over m log m over n. Uh, in this case, we're kind of hinted to the solution from that folk wisdom. We know that for the discriminative classifier, uh, there's a linear relation between m and n, or that m equals O of just n, n to the 1, maybe. This implies a linear equation between m and n, or m is less than or equal to c of n, where c is a coefficient that's greater than 0. This can also be written as m over n is greater than equal to c. Plugged into the growth equations O of m and n function, we have O of the square root of n over m log c. We could reduce the log c out because constants reduce to 1 in big O terminology. So it's a square root of n over m. And if we use the other division of m equals nc, we have n over m is greater than c. And we plug that in. We know c is a constant, so this is greater than our already positive constant. Uh, and so that O is just the square root of 1, or it's O of 1. So from this proof, we determined that since m equals O of n, we know they have a linear relationship uh, for the error. For naive Bayes, it's a simpler process. That error constant as a function is g of O of the square root of log n over m. And that G function is the probability of that the true discriminant function falls near a true class decision boundary. As long as the data checks out and the variables are independent, we get to kind of assume this to be true and go for the O function to do the proof. In this case, it's very quick. M equals log of n, because when m equals log of n, that's root of 1 or O of 1. And so with these two growth rates proven for, we could kind of make this table describing class characteristics of each model. For this regression, it has the lower asymptotic error and the slower growth rate of O of n, which means that you need O of n, you need m O of n samples m in order to reach asymptotic error. For naive Bayes, it's a higher asymptotic error, a lower asymptotic accuracy, but it only needs log of n samples as opposed to n to the first samples. This means that there's two regimes. One in the smaller sample sizes, where naive Bayes actually has a higher accuracy because it's growing faster for its accuracy. And in the second regime, where the ultimately higher asymptotic accuracy of the logistic regression classifier takes over, and that will continue to have the higher accuracy. And we can see these in graphs like these, highlighted all the ones where they showed it in the paper, and they also assume that the ones where you don't see this overlap in the two regimes are occurrences where there's not enough samples for the overlap to eventually occur. This is a closer view up. You can see around an error of bit under 2.5 and number of sample sizes around 55. These lines overlap. The logistic regression classifier becomes more accurate, and you can see on the left is regime 1, on the right is regime 2. For my implementation, I started with the MNIST data set and was going from a range of subset sizing from 50 to 1,000 in intervals of 10. I got something like this, which kind of looks like what we're looking for, but not exactly. It's not very clear. So we recreate the methodology in the paper where we run each sample size randomly some amount of times. And the paper did 1,000 for MNIST. I had to do 20 because that's a lot to run. Uh, but it still looks pretty smooth, something like this. Uh, it resembles kind of what we're looking for. We could kind of see the first regime at the beginning, maybe around 500 samples, and then the second regime for the rest. Uh, but it's not super convincing, especially because we know that we want independent variables for the naive Bayes classifier. But in this case, we're not using independent variables, we're using an image data set where all the pixel variables and their values are very interdependent, because that's how images work. If there's a pixel at the top of the one, there's going to be one below it in order to draw the shape of the one. Uh, so this may be inhibiting the naive Bayes classifier and just giving it a flat line instead of a more true asymptote to approach. It may not even have log n because we don't know if the data is truly interdependent. So instead, I moved on to the one I showed you before, and I created the ionosphere data set. This is 34 variables of radar signals detecting objects in the ionosphere layer of the atmosphere. One if they detect an object, 0 if they don't. And you can see in these graphs the regimes are describing in the paper. This was also tested with, I think, about 2,000 runs per sample size. You can see in the lower sample sizes, starting from maybe 10, going all the way to about 110 and 120. Gaussian naive Bayes has the lower error and the higher accuracy, and that's just due to its faster growth rate, as a steeper rate at that beginning. But eventually, as this regression catches up, you see that regime switch, and then you just see as the two of them start to reach their true asymptotic errors. For this regression, that's a lower error. But there were some differences statistically between my data and the papers. They seem to use less data sample sizes. Maybe they had a more aggressive train test split. They also had they also had the regime switch a lot earlier, around 50 samples. and a higher total error. And this just could be because how my model is implemented. But I'm still very happy to see the two regime switch. For my case, just to note some differences on implementation, they didn't specify hyperparameters, and I don't know if they optimize them for each model. So I just assume learning rate 0.1, uh, whatever the best 2 to the n batch size was for the model, and a single epoch. So the weights were applied, but only once. Uh, because if you just increase the epochs, then it's going to get way more efficient and effective than naive Bayes, and you can't really compare anything. Uh, the other big difference is that they use min-max scaling for both classifiers. And when I try to do that, it really disproportionately affected logistic regression. And I couldn't really see any helpful results. So I use standard scaling instead, with small e smoothing. For my conclusions, despite some numerical differences between my ionosphere model and the papers, I was really happy to see the regime switch happen, and I was able to recreate the phenomenon. I think it's really useful knowledge to know that at those lower sample sizes, generative classifiers could be a lot more effective and quite useful. And that's my presentation. Thank you very much.